Take a moment, look around you. What do you see? Really see? Maybe a table, solid and dependable, a cup perhaps filled with a comforting warmth, or the screen you're watching this on, a gateway to countless worlds. Our eyes reveal a detailed world, a vibrant tapestry of shapes and colors, but it's just the surface, a mere reflection of a deeper reality. We miss the countless tiny stagehands, the unseen forces working tirelessly behind the scenes, orchestrating the world as we know it. Our senses have limits, inherent constraints. They define the boundaries of our reality, the edges of our perception, but science lets us see beyond those boundaries, pushing the limits of what's possible into a hidden cosmos, a universe of the infinitesimally small on a scale that defies intuition, challenging our understanding of size and space. Imagine a single grain of sand, ordinary, unremarkable, about 1/10 of a millimeter across. Barely perceptible. That's the limit of our unaided vision, the threshold of what we can discern. Anything smaller begins to blur into invisibility, or is fading into the unseen. A human egg cell is about this size, a marvel of biological engineering, the largest cell in the body, a world unto itself, right at the edge of what we can see, a frontier of perception. We live surrounded by things just beyond this threshold, teeming with activity, an entire world out of focus, waiting to be discovered. Dust motes in a sunbeam are tiny worlds, miniature ecosystems, but giants compared to where we're headed. The realm of atoms and molecules. Our journey now requires a new kind of vision, a shift in perspective, one guided by science and imagination, fueled by curiosity and wonder. We're about to shrink down, to become infinitesimally small past the limits of our eyes, beyond the realm of ordinary sight, into a realm where the rules of our world start to bend, where quantum mechanics reign. To appreciate this journey, we need a new map, a new way of measuring, micrometers, the scale of cells and microorganisms, nanometers, the domain of molecules and atoms, and even smaller scales where the very fabric of reality is woven. Each step is a leap 1,000 times smaller, a quantum jump, a plunge into deeper layers of existence, into the heart of matter. We are explorers, venturing into the unknown, venturing into an inner space as vast and mysterious as the cosmos, full of wonder and surprise. The questions we ask, the fundamental inquiries: what are things made of? What is the nature of reality? What are the ultimate building blocks? The fundamental particles are ancient, echoing through the ages. Today, we have the means to find some answers, to unravel the mysteries of the universe. So take a deep breath, prepare yourself. The journey begins now into the heart of the unseen. Let's see how deep the rabbit hole goes and what wonders await us. Our first leap takes us beyond the realm of the visible, a journey into scales far smaller than we can perceive with the naked eye. We'll venture past the seemingly substantial grain of sand and plunge into the intricate and fascinating microscopic realm. Here, under the lens, a single human hair transforms, becoming a colossal pillar, a structure of surprising magnitude. It measures about 70 micrometers thick. In this world, it's not just a strand, it's a landmark, a testament to the relative scale of things. Now let's shrink 10 times smaller and we reach the bustling world of living cells, the fundamental building blocks of life. A red blood cell, responsible for carrying oxygen throughout our bodies, is about 7 micrometers across. Millions upon millions of these cells fit within a single drop of blood, a testament to their tiny size and incredible abundance. Even smaller still are bacteria, such as E. coli, measuring just a couple micrometers long, veritable submarines navigating this tiny watery ocean. Trillions of bacteria, a vast and diverse ecosystem, live inside you, playing a crucial role in helping digest your food and maintaining your overall health. Now let's shrink 10 times smaller once again and we enter the enigmatic realm of viruses, entities that blur the line between living and non-living. The influenza virus, responsible for the seasonal flu, is only about 100 nanometers across. Hundreds of these viral particles could fit inside a single bacterium, highlighting their incredibly small size. Viruses, in essence, are packets of genetic information, essentially inert and unable to replicate on their own until they hijack the machinery of a living cell. To even begin to see and understand this world, we needed to develop entirely new tools and technologies. The light microscope, a revolutionary invention, revealed the existence of cells and bacteria, opening up a new frontier of biological understanding. However, light's inherent wavelength sets a fundamental limit on its resolving power. To truly see viruses and the intricate details of the nanoscale world, we needed electron microscopes which use focused beams of electrons instead of light. This allowed us to resolve these incredibly tiny structures with unprecedented clarity and detail. These powerful tools have opened up a hidden universe, revealing a world far more complex and diverse than we ever imagined. The microscopic world is teeming with life, activity, and endless mystery, a vibrant ecosystem existing all around and even within us. And this is just the beginning of our exploration. We're just getting started in unraveling the secrets of this hidden world. We go deeper, leaving biology for the realm of chemistry. Shrinking past viruses, we reach molecules, tiny structures that build everything. A water molecule, H2O, is less than a nanometer across. Trillions fill a single teardrop. Molecules are in constant frantic motion. Heat is their dance, cold is when they slow. DNA is a giant molecule, 2 meters long if stretched out, yet packed into a cell nucleus. This single molecule contains the instructions for building a human, but molecules are made of atoms. The word atom means uncuttable. Once thought to be the final building block, for centuries atoms seemed indivisible. But the universe had another surprise. Atoms are not the end of the road, they're just another door. The journey continues into the very heart of matter. What lies inside an atom? Let's find out. The next layer is stranger still. Welcome to the atomic world. Let's embark on a journey shrinking down, past the familiar world, past the microscopic, all the way into the atom itself. And what do we find? Mostly empty space. It's quite astonishing, really. The atom, the fundamental building block of everything we see, is mostly nothingness. To give you a sense of scale, if an atom were a cathedral, a massive, awe-inspiring structure, its nucleus, the core of the atom, would be a mere grain of sand, sitting almost invisibly at the very center. And the electrons, they don't orbit like planets. Instead, they exist in a fuzzy cloud of probability, a haze of potential locations, not neat, predictable orbits. Welcome to the strange and fascinating world of quantum mechanics. A typical atom is incredibly small, only about 1/10 of a nanometer across. That's 1/10 billionth of a meter. To illustrate just how many of these tiny particles there are, consider this. There are more atoms in a single glass of water than there are glasses of water in all the oceans of our planet. Think about that for a moment. Atoms are truly the fundamental building blocks of reality, the tiny bricks that make up everything around us. The nucleus, residing at the very center of the atom, is what defines the atom's identity, dictating what element it is. Hydrogen, the simplest element, has a nucleus consisting of just a single proton. Helium has 2 protons in its nucleus. Carbon, essential for life, has 6. And gold, prized for its beauty and rarity, has a whopping 79. The number of protons, also known as the atomic number, is what definitively determines the element and consequently dictates its unique chemical and physical properties. The periodic table, that iconic chart in every chemistry classroom, is simply a list of all the known atoms, meticulously ordered by their number of protons. Electrons, with their negative charge, are held in place around the nucleus by the electromagnetic force because, as we all know, opposite charges attract each other. But here's a puzzle. The nucleus itself is packed incredibly densely with positive protons. Shouldn't they be repelling each other with tremendous force? They certainly should. And they would if it weren't for the strong nuclear force which acts like a super glue, holding them all together. This force is immensely powerful, far stronger than electromagnetism, but it only works at incredibly tiny distances within the nucleus itself. The atom, therefore, is a place of immense contained power, a miniature powerhouse of energy. It's a delicate and intricate balance of these fundamental forces constantly at play. The atomic world, though invisible to our naked eyes, is both incredibly elegant and profoundly strange, defying our everyday intuitions. But even with all that we've learned, there's still so much more to discover, so many mysteries waiting to be unraveled. So let's continue our journey and dive even deeper, right into the heart of the atom, into the nucleus itself. The nucleus holds protons and neutrons, nucleons unbelievably dense and tiny. A proton is about a femtometer across 1/1000th of a nanometer. Protons and neutrons give atoms almost all their mass. Neutrons are neutral, slightly heavier than protons, and help glue the nucleus together. The number of protons defines the element neutrons create different isotopes. For a long time, protons, neutrons, and electrons seemed fundamental, but smashing protons together revealed a zoo of new particles. Protons and neutrons couldn't be fundamental, they had internal structure. They are composite particles made of something smaller. The journey wasn't over. We had to look deeper into the heart of the nucleus. What are protons and neutrons made of? The answer changed physics forever. Let's go to the next level. Enter the world of quarks. Inside a proton, we find a wild dance of quarks, 2 up quarks and 1 down quark. Neutrons are 1 up and 2 down quarks. Quarks are bound by the strong force carried by gluons, cosmic rubber bands that never let go. You can't isolate a quark, they only exist in groups. As far as we know, quarks are fundamental, no size, no internal structure. But quarks aren't alone. Electrons belong to another family, leptons. There are 6 types of quarks and 6 leptons, including the electron, muon, tau, and 3 neutrinos. These 12 particles, plus force carriers like gluons and photons, make up the Standard Model. The Standard Model is our best description of the universe's workings. It's been tested with incredible accuracy. Every particle and force, except gravity, fits into this elegant chart. As far as we know, quarks and leptons are the smallest things, the indivisible letters of the cosmic alphabet. Is this the end? Are quarks and leptons the final answer? Maybe. Science is about asking the next question. Our most powerful tools, particle accelerators, smash particles together to reveal what's inside. To see smaller things, we need higher energy. Shorter wavelengths. Probing inside a quark would require an accelerator the size of the solar system. But there's a deeper limit. The Planck length, about 1.6 x 10 circumflex 35 meters. If an atom were the size of the universe, the Planck length would be a tree. At this scale, physics breaks down. Quantum mechanics and gravity clash. Observing this small would create a tiny black hole. Space and time might lose their meaning, becoming a bubbling quantum foam. This isn't just a technological limit, it's a theoretical one. The Planck length is the edge of the known map. Beyond it lies the unknown. What lies beyond the Planck length? Here we enter the wild world of theoretical physics. String theory proposes that fundamental particles are tiny vibrating loops, strings. Each particle is a different vibration, like notes in a cosmic symphony. String theory requires extra dimensions, 10 or 11 curled up too small to see. Imagine a garden hose. From far away, it's a line. Up close, it has a hidden dimension. These extra dimensions could be all around us, just tightly curled. Another idea, quantum foam. At the Planck scale, space-time is a bubbling soup. Tiny wormholes and virtual particles flicker in and out of existence. Space-time itself may be quantized, not smooth. The smallest thing might be the pixelated fabric of space and time. These are mathematical dreams for now, but they hint at a deeper reality. The quest continues. We've traveled from a grain of sand to the edge of reality. Why does this journey matter? Because the story of the small is the story of the universe. The laws and particles we discover shape the cosmos and our origins. The balance of forces makes stars, planets, and life possible. Our quest for the small gave us technology. Transistors, computers, lasers, MRI, nuclear power. Curiosity-driven research changes the world, but beyond technology, this journey fills us with wonder. It connects us to the universe on the deepest level. To know you're made of stardust is one thing, to know your atoms are tiny universes is another. The quest for the smallest thing is a human adventure, reminding us there are always new frontiers to explore. The cosmos within is as vast as the cosmos without.